So we established last time that the three things that are preserved by a black hole are mass, electric charge, and angular momentum. So what does this mean? It means that as things fall into a black hole, if they carry angular momentum, then the black hole gains that angular momentum. So imagine we have a black hole, and it's rotating in this direction. And we know that things with gravity, like a star, can warp light. We talked about that in day 4. So it does that because it actually warps space and time around it. So what happens when you have a black hole so intense in its gravity that it really starts to warp space-time? This is where things get really cool. For a while, we thought that the only possible way that we were going to see any angular momentum or be able to detect a black hole was from something called the accretion disk. If you get a rapidly rotating black hole, which is entirely possible, remember, most black holes are the corpses of large dead stars. So a star is rotating. It runs out of fuel. Without that fuel, it's no longer generating energy and heat from within to prevent collapse under gravity. It collapses rapidly. Some of that mass slams together, spews out in a supernova. And that dust scatters through the solar system and the galaxy. But if there's enough left over, it forms a black hole. But it's a black hole formed from something that used to be rotating. So that black hole is also rotating. It retains that angular momentum. So we now have a rotating black hole in a region that's filled with dust left over from that supernova. Well, as things fall in under gravity, if they're not fast enough to escape, they'll come to the black hole. And they'll form what's known as an accretion disk. As they rotate, they start to give off energy. Some through black body radiation, some because they're electrically charged, but they will start to give off radiation. This accretion of materials forms what we call an accretion disk. And this disk actually can be visible if it's giving off enough black body radiation to be in the visible spectrum. So for a while there, we thought that that was how we were going to spot our rotating black holes. But we found out so much more as we started digging into it. So imagine you have a top-down view. And your black hole is rotating in the counterclockwise direction. Now, from the frame of reference of a particle coming in this way, we have to ask ourselves what's going to happen. So let's say we have a powerful flashlight and we beam the light over here. We can easily imagine this bottom beam of light getting warped in and wrapping around. But what about this light here that's coming and the black hole is going the other way? That experiences something called frame dragging. If a black hole is spinning fast enough, it can pull space and time around it so hard that it becomes impossible to rotate around the black hole opposite to the black hole's direction of rotation. Anything approaching that black hole will be forced to rotate around it in the same direction the black hole's rotating because it's dragging space and time with it to the point where it's impossible to escape. So this is one of the surprising areas that we found. It can actually warp space-time so much that there's nothing you can do to stop it. And this actually leads to Neil deGrasse Tyson's preferred manner of death if he gets to choose when the time comes. It's a highly technical term called spaghettification. Because if you have an object that approaches a black hole that is rapidly rotating, well, that rotating object, or that object falling in, starts rotating along with the black hole. But that effect increases dramatically as you get closer. So as you start to cross this line, the back end of the object looks the same, but the front end is being subjected to a very strong pull of gravity. It's like Play-Doh being squeezed in that direction. And as things fall in further and further, it gets stretched out more and more. So the technical term is spaghettification, because it doesn't matter what shape you have when you fall in. By the time you're done, you're shaped like a long, thin strand of spaghetti. It would not be a pleasant death. But hey, if an astronomer wants to choose his own manner of death, he's going to choose one that puts him out in space and face to face with a black hole. Some of that may be because of some very weird effects. We talked about time dilation and how time slows down with a moving clock. It also slows down in the presence of a strong gravitational field. That's one of the other side effects of relativity. So while technically you'd think being stretched as thin as spaghetti would be a horrible way to go, from your perspective, it would be a very, very long time coming because of how slow time would become for you. So you'd think that would drag it out, but what really would happen is that you would see the universe around you kicking too fast forward. At least you'd try. The problem is the light from that universe that you'd be observing also gets swept up in this pattern. So it would have to be catching up from you or with you from behind. And that's another thing that gets a little weird when you have a rotating black hole. Let's say you're not completely spaghettified yet, and you had the presence of mind to bring a flashlight with you. Well, when you turn that flashlight on, that light travels around the black hole and comes around from behind. So you wouldn't be able to see anything in front of you because the light is traveling the same direction you're going. If you really planned ahead and you dove at that black hole feet first and had your flashlight pointed down, when you look ahead, what you're going to see is the bottom of your own feet as that light wraps around the black hole and comes back to meet you face first. So if you're going into a black hole and want to see anything, you've got to go feet first and look behind you. And then you might be able to see what's ahead of you.